Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. Today, I want to talk to you about rules of inference in particular, and the rules that we use for developing our proof systems. Now, we've got a couple of rules that we take as basics, certain propositional rules like uniform substitution, modus ponens, and then the rule of necessitation, our specifically modal rule that says if you have a theorem, you can put a box on the front of it, and the result is also a theorem. We've also talked about a number of other rules, these things that we call derived rules, because they don't really add anything to our logical system. They just allow us to do proofs in fewer steps. They're shortcuts. They're derived because we can give derivations for them. And for most of them, we either have or I've left it as exercises to the viewer. But think more broadly about what it is that we are doing with rules of inferences, because there are loads of rules that we could add which would change the sort of things that we are able to derive. So without necessitation, we would not be able to get from some individual formula to that formula with a box on it unless we have other rules and other axioms in our axiomatic basis, as we saw when we looked at alternative axiomatic bases for K. So one thing that rules can do if we add rules to a system is they allow us to prove more things. Derived rules are not of that sort because everything that you can prove with a derived rule, you can prove without, because we have these little derivations that they are just shortcuts for. But there's another class of rules that we might be interested in, which are not necessarily ones that we can give alternative derivations for, but nevertheless, when we add them to our system, don't allow us to prove things that we couldn't already prove. These rules are called admissible. The reason that they are admissible is because we can admit them to our logical system without turning it into a different system. So that's the key point. We don't want to suddenly be able to generate more theorems because then we don't have the same logical system. We have a different logical system. Because remember, we always are thinking of logical systems essentially as the set of theorems that you can prove from a relevant axiomatic basis, i.e. axioms, plus rules of inference. So what I want you to come away with from this video is this notion of a distinction between kind of setting aside the rules that we just take as basic, two types of rules that we can add to our logical system which don't change it. They don't allow us to prove new things. These are the derivable rules, which we've seen examples of, and then there are admissible rules, which we will see examples of. So I'm just going to give you kind of formal definitions for when something is a derived rule and when something is an admissible rule. So let's get our whiteboard up. The first one is this new notion of an admissible rule. So we have a logical system S. So let S be any system. And then we've got formulas, phi 1 to phi n, and then just plain phi, be formulas in the language of the system that we have. So these are, we're speaking about these in the context of modal logic, but these are definitions that apply more broadly to any kind of logical system you might be interested in. So just a bit of notation. So we will denote an arbitrary substitution of any of these formulas. So the phi 1 to phi n plus phi by e.g. phi with s in brackets. So that is just some substitution instance. So then if we have a rule of the following form, so a rule of the form, if the conjunction of phi 1 to phi n is a theorem, then phi is a theorem, is going to be admissible in S, because admissibility is always with respect to a particular logical system. Some rules might be admissible in one system and not admissible in another. And in fact, we will see an example of this. So a rule of this form is going to be admissible in S if every substitution instance phi1 s all the way up to phi n s, and of course also our kind of conclusion or a consequent formula phi s. So for every one of these substitution instances of the original formulas, so of phi1 to phi n and phi s, actually, let's focus just on phi1 to phi n. So every substitution instance of these formulas is a theorem of S only if the substitution instance of the conclusion of the rule is a theorem of S. So what this means is that you can have a rule be admissible in your system if whenever you take any substitution instance of the formulas that form the conjunction of the antecedents of the rule, if those things are theorems, then it follows that the substitution instance of the conclusion must also be a theorem. And we can contrast this with the notion that we've already seen examples of, namely of a derivable rule. So again, this is for any system whatsoever. So let S be a system and phi1 to phi n and phi be well-formed formulas in the language of the system. Then we will say that a rule of the form if the conjunction of phi1 to phi n is a theorem, then phi is a theorem, is derivable in S. Again, this is always going to be with respect to a particular system, because you can derive some things in some systems that you can't derive in others. So a rule will be derivable in a system S if there is a proof of phi from assuming that phi1 all the way up to phi n, their conjunction, is a theorem of S. And this is what we have seen with all of the derived rules that we've had so far. So admissibility is about substitution instances. And if all of the substitution instances of the antecedent of the theorem are members of the system, then every substitution instance of the consequence of the rule must also be a theorem of the system. Derivability requires us to be able to give a proof of the consequence formula from the antecedent ones. Now, I've got a lot more to say about admissible and derivable rules, but I'll save that for the next video. We will look at, well, what is the relationship between admissibility and derivability, and then see some actual examples. So join me then for more about rules. And until then, take care. Cheers.